Hello, in this video we will talk about the pH of salt solutions. And so this is an extension of the conjugate acid-base pairs video that came previously. And so it might help you very much to go back and review that video before you continue with this one. Okay, and so the main moral of the story from that previous video is, okay, you have an acid and it'll donate the proton to a base, and then, alright, on the other side of your equation, then the hydronium here, functioning as the conjugate acid, will donate that proton back to the base. So we have these conjugate acid-base pairs. So acetic acid on the left and acetate on the right are a pair. And then the water is the base, and the H3O+, the hydronium, is the conjugate acid. And so before, we were just looking at what happens when you put this acid into water. What is the pH? But now we're looking at what happens if you put just the conjugate base into water. The conjugate base of a weak acid is actually a base, and it'll make your solution basic if you put it into water just by itself. And so that's what we're going to talk about here. So the overview of what we're going to say is, first of all, don't forget what a salt is, right? So you have a strong electrolyte, put it in water, it dissociates into a positive cation and a negative anion. Okay, it's a salt. And then salt hydrolysis is when you break water apart. So hydro is water, lyse means to split or break. And so hydrolysis, you're going to take the water and break it apart, make H+, make OH-, depends on whether you have an acid or a base. The way I think of it is that your anion or cation, whatever you have, it messes up the pH of water. It affects the pH of water and makes it either acidic or basic depending on whether it's a acid or base. And so this comes down to Ka, Kb, the conjugate Ka, the conjugate Kb, things like that. The overall thing here is that if you have a strong acid, its conjugate base is ineffective as a base. If you have a strong base, its conjugate acid is just ineffective. Now, if you have a weak acid, however, its conjugate base is actually basic. And so if you put just fluoride in water, you'll get a basic solution. Then if you have a weak base, its conjugate acid will actually function like an acid. So let's get into that with more detail. So, strong acids first. So here's the equation for hydrochloric acid being a strong acid. So here's the strong acid, here's its conjugate base, and it produces H3O+ in water, so that means it's an acidic solution. Now if you were to take just that conjugate base and put it into water, this conjugate base doesn't affect water at all. It doesn't change the pH. And the reason is, its Kb is ridiculously tiny. So remember, to find Kb, you take Kw and divide by Ka, and so here's Kw, and then this is the Ka of hydrochloric acid. It's positive 6 because it's a very strong acid, and when you do this, your Kb is super small. So whenever Kb is less than 10 to the negative 14th, it's not going to affect the pH of water at all, because 10 to the negative 14th is the auto-ionization of water into H+ and OH-, so if your Kb is less than that, water's doing it on its own without you, and so you don't really need the base. And the base doesn't do anything. Alright, on the flip side, if you have a strong base, so here's our strong base, right there, then you put it into water, you get the conjugate acid, and it makes hydroxide because it's a base. So if you put just that conjugate acid into water, the sodium, it's not going to affect the pH of water at all. And so the same logic applies. The Kb of the sodium hydroxide is so strong, that means the Ka of its conjugate acid is ridiculously small, and it doesn't actually function like an acid. Now, we have weak acids, and so things are going to be different here. So you have your weak acid, and then put it into water. It makes the conjugate base, and hey, it's an acid, so it makes H3O+. Now, if you take just that conjugate base and put it into water, then something's going to happen. That fluoride will hydrolyze water. It will take the proton off of water, it'll pull it off, and it'll leave hydroxide. And it'll make a basic solution. And in this example here, we're focusing just on the fluoride. It's paired with the sodium because you can't just drop a negative ion into water. You need the positive ion as well. And I picked sodium because on the previous slides, we said that sodium itself doesn't affect water. So we can focus just on the fluoride. Okay, so let's put some numbers on this. So remember, Ka times Kb equals Kw. And here's the equation for the weak acid again, just from the previous slide. Here's its Ka. You would find it either in the problem or in a table somewhere, something like that. Here's the equation from the previous slide for a conjugate base. And well, we want to solve for Kb. So you divide Kw by Ka, and then it gives you the Kb for just the fluoride anion. And now this number is bigger than 10 to the negative 14th, so it means it's actually going to function as a base. Okay, here's the flip side. So if you have ammonia, which is your weak base, then put it in water. Here's its conjugate acid, and it's a basic solution because it is a weak base after all. And so now if you put just that conjugate acid into water, and I'm pairing it with chloride here because we saw previously that chloride doesn't affect the pH of water. So the ammonium, though, NH4+, it will function like an acid. It will make H3O+ by donating a proton to the water. And so this becomes acidic. And so if we want to see what the Ka for this conjugate acid is, we take the Kb of ammonia underneath the Kw, and then we'll see that we get 5.6 times 10 to the negative 10th, and that is bigger than 10 to the negative 14, and so this is going to function like an acid. All right, so now let's do a problem with this. So say I'm going to go back a little bit to the sodium fluoride. So this is the conjugate base of a weak acid. What's the pH of a solution of sodium fluoride? 0.25 molar. And then here I'm giving you the Ka for the acid, right? So the big thing in these problems is you have to switch from Ka to Kb and whatever, depending on whether you're starting with a weak acid or a weak base. So here we're interested in the fluoride. That's the conjugate base of a weak acid. So we'll have to use this Ka, turn it into Kb. Well, first let's start here. So the sodium fluoride will dissociate in water. So we have the cation and the anion. And then it's good practice to look at both of these and think about whether they're going to affect your pH. The sodium is not, because it's the conjugate acid of sodium hydroxide, which is a strong base. But the fluoride will, because it's the conjugate base of a weak acid. All right, so we don't really care about the sodium, but we do care about the fluoride. So, all right, we need to find the Kb. We did this math on a previous slide, but I want to put it here just to remind you that you'll have to do this math when you do the problem. So here's the Ka of HF. Kw divided by Ka gives you Kb. Okay. Now we have Kb, and it's off to the races. We're going to do an icebox just like old times. And so remember, the Kb and the fluoride, you do the normal base thing, right? Kb means this specific type of equilibrium expression, where you have your base, it makes a conjugate acid, etc., etc. Now something different here is that the base is negatively charged and its conjugate acid is neutral. Whereas before, with weak bases, say ammonia or something, it was neutral, and then it went to positively charged. So the overall charge still changes. It still goes up 1. Here it just goes from negative to neutral. Just a little difference, otherwise still the same thing. You're going to put this in an icebox. And, all right, here's the initial concentrations. We just start with the fluoride and 0 of the other two. It's shifting to the right. Here's the equilibrium line. And then now we're going to do just like we've done so many times before. We're going to take this equilibrium line, plug it into the form of the equilibrium constant expression, in this case Kb, because this is the base dissociation equation. Plug that in. Great, now we need to solve for x. Step 1, let's try neglecting x. It's easy, and if it works, it makes our life great. So let's try that. You do that, you solve for x, you get this number, 1.87 times 10 to the negative 6. Well, turns out 1.87 times 10 to the negative 6 is such a small portion of 0.25 that this is a great assumption. So we're going to use this, we're going to take this value for x, it'll be perfect. Now you have to think, what the heck does x mean? let's see here. X is, what is it here? Oh, it's hydroxide. So we need to worry about that. So X gives us hydroxide. Okay. So X gives us the concentration of hydroxide. Perfect. Is that what we want? No, we want pH. Okay. So we have to work with that. Easiest way to do this, in my opinion, is to find the pOH first by taking the negative log of the concentration of OH. This gives you pOH. And then 14 minus pOH gives you pH. And then this solves your problem. So when you're doing this problem, take the salts, the sodium fluoride, dissociate them, think of what's going to do what. Oh, the fluoride. Find its Kb, which will be a little bit of work. Then do your normal icebox. And then in this case, X gives you the concentration of hydroxide, so then you have to convert that to pH. Now, next problem. What if both the cation and the anion hydrolyze, split water, function like an acid or a base? What's going to happen here? And really, it depends on which one's stronger, right? And so we're comparing the Ka for the conjugate acid, which you'll have to convert from Kb for the original weak base, and then the Kb for the conjugate base. Again, you have to do the conversion there. And so whichever one's stronger wins. Whichever one's bigger is going to win. And so if your Kb is larger than Ka, it means your solution's basic. The anion, the basic thing, hydrolyzes more than the cation. Okay. And anions tend to form basic solutions because they can accept a proton pretty easily. The reverse is true. If you have Ka bigger, then your solution's acidic. And if they're about the same, then your solution's neutral. So let's use ammonium fluoride as our example. And I'm going to do this math again for the third or fourth time in this video, just to show you that you generally have to do this process when you're trying to figure this out. So you look up what the Kb for ammonia is, convert it to Ka for ammonium. Similarly, look up the Ka for hydrofluoric acid, and then convert it to the Kb for fluoride. Now, let's see here. 10 to the negative 10th is bigger than 10 to the negative 11th, so that means this solution's acidic. All right. Hold the phone. If a weak acid makes a base, how does it function as an acid? Right? Like, you got your acid, hey, it's going to make a base. What's happening here? So, turns out that the Ka for this weak acid is much bigger than the Kb for the conjugate base. And so, just like on the last slide, the Ka wins, this thing's going to be an acid. Which, okay, makes a lot of sense. Now, one last example problem. Let's do the pH of ammonium chloride. So we're working with the conjugate acid of a weak base. All right, here's the Kb for the weak base itself. What are we going to do? NH4Cl, ammonium chloride, dissociates in water. And the chloride is not going to affect the pH at all. So we just worry about the ammonium. And it's half molar. All right. So now we need to find what its Ka is. We know its concentration. I've done this several times in this video, so I'll show it here again. All right, now we have Ka. We treat it like an acid. So you put the acid in water, it makes hydronium and whatever's left by moving the proton from the acid to the hydronium. Put it in an icebox. Here's the initial concentrations. Moving to the right, here's the equilibrium line. And now this is just like any acid-base problem. So we take the Ka that we found and plug it into this equation, which is specific to the acid equation we have above. All right, now we need to solve for X. Start by neglecting it. You get this number for X. Now you need to check your assumption. Turns out this number is much smaller than 0.5, which it's subtracted from. So this is a perfectly valid approximation. All right. Now we take X and then think of what does X mean. X is hydronium. Oh, that's going to be easy. Okay. So X is hydronium. And then you can find pH from that by taking the negative log of the concentration of hydronium. And then there's your answer, pH. Okay, so that's really all we have for now. I'll end with the summary, right? That when you have the conjugates of strong things, you don't have to worry about the pH changing. When you have the conjugates of weak things, then you have to treat them like their own acid or base and then deal with that. All right, thanks for watching.